Okay, differential equations. We've got our last lesson of chapter 6. Very exciting to see that. 6.2, we've got day 3. We're going to have more solutions about singular points. What we saw is that from yesterday, we'd always make an assumption that if we had a regular singular point, we all of a sudden said, well, wait a minute, we are actually going to assume that we had a series in this style, that we'd have sigma from n equals 0 to infinity of c sub n x to the n plus r. And the r's actually really did come into play, and we said that you could even factor that constant of x to the r out. And that really is something that we wind up doing at the end, that we should do at the end. And but what we're seeing is, as we're solving for what r could equal yesterday, and what we'll have for another problem, just one problem assigned today, what if r1 and r2 are different and they do not differ by an integer? In other words, when you subtract them, you don't get an integer. And yesterday we saw that r was 0 and r was a fraction. I forgot what the fraction was. Was it 2/3 or 3/2? One of the two, I think. And, in that regard, when you subtract those r's, take their difference, that's not an integer. Then you can go ahead and find your two linearly independent solutions. This is what we did yesterday. So that's all well and good. But there are two more cases that we're going to investigate. And guys, for these two cases, this is going to be quite a bit of a switch here. You can see the possible answers coming up. Let's just say r1 and r2 are different, but they differ by an integer. In other words, you subtract your r's and you get an integer. Then you get two linearly independent solutions, but look at the second form here. That might be the big surprise. You might think, oh my word, it's one thing to see the n plus r sub 1 here. You've got your n plus r sub 2 right over here. But my word, is you're wrestling with this thing. Wow, you're seeing a natural log come up multiplied to your first series, and you've got some other constant out there, and that just begs the question, how in the world would you even find a second form like that? Where's that natural log coming from? We'll be talking about that in a little bit. Case 3, what if your r's actually are equal to each other? Well, this is going to look remarkably close to what we just talked about. Yes, you'll get your two very different series here. However, what you're going to see very quickly is this, that you'll get a second form where you get a y1 natural log of x once again, and you can see that your counter is just a little bit off there with sigma. If you're really paying attention, you're going to say, oh, it's identical to what we just saw earlier. Well, the big difference is that, here we'd go from n equals 1 to infinity as opposed to n equals 0 to infinity. And, we're not going to see a case 3 in action today in the notes. We're actually going to look at case 2 more right now. So we're going to get started actually solving this thing right here, x, y, double prime plus y equals 0. And by the way, we're going to cross out the back page. The back page, number 19, we were going to do that problem. There will only be one homework problem. It will be number 19. It's pretty much like what you did yesterday. It's the same exact style. In other words, number 19, you can expect to be case number 1. Okay, so we could try to get some practice with this. You're going to work ahead. A lot of times you don't know what case you have. You have to solve for r. And guys, that's what we're going to do right now. So let's go ahead and get started with that. And real quickly, we're going to more or less just say, how did we even begin? Well, this has a surprise to it. We're going to say, look, let's assume that we had y equals from n to 0 to infinity. We had c sub n, but we have this x to the n plus r. Remember, that was the big twist that we saw yesterday. And then we could take y prime, and we could say, wow, if we had y prime, we'd take a derivative. But like we said yesterday, you're taking the derivative of your smallest term when n equals 0. You'll have x to the r. And guys, that very well is not a constant. We are not guaranteed that we're losing that term for n equals 0. So I can't just go to n equals 1. So we're reviewing this general setup that we did yesterday, and that's great. I think it's wonderful and necessary, mind you, to be able to do that. And then finally, as we take a second derivative, same thing. As you look at the 0th term, we have no guarantee that that 0th term happens to be a constant. So once again, we're not at our freedom to just go to n equals 1. But what we are going to be able to do is bring down one more term from a derivative. So I'll bring down an n plus r minus 1. And then up here, we're going to lose another. We'll have, this is now going to be n plus r minus 2. And what we will do, of course, is substitute these two in here. Now, forgive me for not even addressing the real issue beforehand. First off, I do think it's super, super, super important to know that you don't always just start with this x to the n plus r. Forgive me for rushing into that. What really requires, what do we see in this problem where we'd say, you know what, I will need to have this extra plus r factor? What's driving this whole new process? A regular versus an ordinary solution, or a regular singular. You can see right here at x, if x is equal to 0, we're in trouble, aren't we? We're in trouble. So we could see that x equals 0 is a regular singular point. How do we know it's regular? Well, if we were to divide, and we could do that up here too, and we will do that in due time. If we were to divide everything by x, 0 divided by x, we'd have this. We're guaranteed that x minus 0 just shows up once in front of y prime in that denominator, and it can show up twice in terms of the denominator in front of the y. So we do have a regular singular point. That means we do need to deal with this n plus r. So that's so important. We can't just gloss over that. We can't just ignore that. But what's happening? Well, I'm going to say here's my x, and then I'm going to multiply to that this sigma, where we go from n equals 0 to infinity of c sub n, and here's n plus r, and here's n plus r minus 1, and here's your x to the n plus r minus 2. And then we'll say plus my y. Well, my y here is thankfully pretty straightforward. We'll just have this thing right here. And as I multiply my x in here, I think you can see very, very quickly that we'd have a c sub n, n plus r minus 1. And here you'd have x to the n plus r minus 1. And, thank goodness things are moving right along. Maybe you remember yesterday that we really wanted to make a move and we wanted to do some cleaning up. You could factor out that x to the r. That's the brand new foreign look here that looks so different from what we were doing earlier. So you know what, guys? Go ahead and pull an x to the r out of both of your sigmas. And, as you do that, well, it's going to get cleaned up just a little bit more. And every little bit is, of course, a help. I'll just have an x to the n minus 1, because I'm losing that r right there. And then in this second sigma, I'm going to lose that r. I'll just have x to the n. And guys, right here you can pretty much see, outside of just seeing an r right over here, and over here, of course, it's looking remarkably close to what we had earlier. Now, what we did the other day is we said, hey, we want to have the exact same powers inside of our sigmas. We definitely want to do some cleaning up. So we've got our x to the r out here. If I were to plug in n equals 0, guys, what's my lower bound down here? I'm going to have k goes from -1. Wow. That's pretty common as you're working out the method of Frobenius. And then if solving for n, you'd get k plus 1. So I'd get c sub k plus 1. And then, like I said, we'd have a k plus 1 instead of n. So that's k plus 1 plus r. If you're really on your toes, you're going to say n minus 1 itself is k. So you'll have k plus r here. Of course, if you would have plugged in, k plus 1 in its place, the plus 1 and the minus 1 would have canceled it out. So here we'll have our x to the k. Hey, this second term right here is so much easier to work out, the second series. As I go ahead and I replace n equals 0 here, I'd get k equals 0. Then we'll go up here to infinity. We'd have c sub k and x sub k. So, hey, things are working out all right. We're getting there. You look and you could say, well, at least the insides are so much nicer. We've got x to the k for both. But I hope what is really, really jumping out at you and is more than a little troubling is you could say, oh my goodness, really? We've got this k equals -1. How do we deal with that? Well, we're going to truncate that little term off. We're going to evaluate what happens when we plug in k equals -1. And we're only going to have to do it to our first term, this first summation. So when I let k equal -1, -1 plus 1, you would get c sub 0. And, as I plug -1 in here, -1 plus 1 is 0 itself, so I'd have 0 plus r. So I'd have an r over here. And then k being -1, I'd have r minus 1 over this way. I'd also have x to the -1. So that's what we get when we plug in k equals -1. Guys, from there, you're going to notice that the two counters will be identical. They're going to be one and the same. They're both going to go from k equals 0 to infinity. And now what? Now we can join these into one summation. I can even factor that x sub k out, and we'll do that actually in a moment. So we'll have our c sub k plus 1. Here's a k plus 1 plus r and a k plus r. And then I'll even say a plus c sub k. And you could even put these brackets right here and say here's your x sub k. And there you go. You're able to really join all that into one summation, and it looks so much better. Well, first off, I hope you're noticing that, right here, all this has to equal 0. This is known as the indicial solution. As you're looking for possible r values, you can see r would equal 0 or r would equal 1. We're going to have two possible cases there. And, then we're going to evaluate. We're going to solve for c sub k plus 1, and we're going to work out some different cases. We're going to do that in just a moment.